May wander in a couple minutes late, as so often happens. It's my pleasure to welcome Peter Wonka back to a youth talk. And many of you remember he was here a couple of years ago giving a talk. Peter's an assistant professor at Arizona State in Tempe. That title will change soon, August 1. Yeah, so he'll be the associate professor the next time you see him. Peter's an interesting guy. We've gone to a lot of the same places at different times. He spent a year in Rennes working, and I've had a research collaboration with him for the past 3 years. I did a sabbatical in Grenoble. Peter did a stint working in the same group, the artiste group with Francois Sillon. And we didn't overlap there either. I've known Peter from his work on urban environments, and it wasn't until I looked at his CV that I realized he actually got it a Master's of Science in Urban Planning. So he can tell what's right and what's wrong with cities.
I can claim.
Yeah, you can claim to tell what's right and wrong with
I'm a licensed urban planner.
So Peter's, you've probably seen a lot of his work at the SIGGRAPH conferences, the VIS conference. He also does work in image process set. I think he's best known for his work in modeling and realization of different urban environments, and he's done some really interesting work with that. He's also not just modern urban environments. He won the Best Paper Award at the VAS conference for modeling and archaeological sites. Now, it's not the VAS conference many of you know. It's the real VAS conference, the Virtual Reality, Archaeology, and Cultural Heritage Eurographic Symposium that used that name many years before I Tripoli co-opted it. But so Peter's pretty well known, and he's going to tell us about his research.
Okay, thanks for the introduction. So I'm going to talk about modeling and visualization of urban environments. Even though visualization, I named the talk more to honor the strong tradition of Utah. It's maybe not that you will recognize it as scientific visualization in the sense of the VIS community. It's more some visualization of what I think should be visualization, maybe. So my background, as Chuck said, we had some overlap. I started out, since some of you might know me, in Vienna, at the Vienna University of Technology. And I originally started to study computer science. And back then it was like after high school, and I had a sister. She was in elementary school, and then my mother complained that I was working less than her for my studies, so maybe I should do something else. That's when I decided to study urban planning on the side. And as you can also see in my research, I loved cities back then. I still love them now, and I really like to work with urban environments, and this is also where part of my interest is coming from. As a student, I was also in Grenoble, postdoc at Georgia Tech, and now in Arizona State. And what you can observe from my career, there's a trend to going from the cold to warmer and warmer weather. But I might have overshot a bit at Arizona State, because now it's a bit hot in the summer, so maybe Georgia Tech was the real optimum there. Okay, so I'm going to talk about modeling and visualization and rendering. And the goal of my talk is mainly to convince you that I'm working on interesting problems. This is a design choice I made. There are multiple ways to give such a talk. I'll keep it at a reasonably high level, and I would like to talk about the problems I'm interested in, not so much about one specific solution to any of these problems. And the idea, partially why I like to do things like this, is because the hope is that you can find at least something that interests you and then go and hopefully maybe read one of my papers, reference my work, or we have something in common when we meet the next time to talk about. Now, I'll start out with a brief review of what I did several years back, maybe in the early 2000s. That was basically starting with procedural urban modeling. And the idea was that, and still, I mean, I feel that urban environments are extremely important. There's a lot of work done. It's from planning, security, architecture, traffic, driving, health. I mean, there's so many things connected to urban environments. So in some sense, I believe that since urban environments are so important, almost anything connected with urban environments is important. And since I did graphics, the main obstacle back then was really there's no tool available for efficient modeling of these environments. And even though I was always interested in rendering, also visualization on the side, in the early 90s, well, like 90s, it was more like 97, 96, there weren't really models out there to do this type of work. So even though I published a lot later, kind of this work started in the late 90s. So how can we efficiently model these environments? And the solutions that we came up with in, published at SIGGRAPH, these were the initial papers, were based on a procedural generation to program, basically program buildings. And the challenge there is how can you somehow encode structural and spatial complexity of architecture to have some efficient creation. And when you start out with basically nothing, the goal is to just create a large city out of nothing that might not be, it's not going to look like a real city, maybe it should have plausible buildings, but you want to create a lot of content really quickly. And there are a lot of applications for this. Maybe I can briefly with this video illustrate the main aspect of our solution. So what you'll see here, it's just the best video we made, is you see a building by an Swiss architect, Semper. This is an observatory. And the building, if you do architecture, you want to start with a mass model and then basically fill in the details. So the mass model you see here is one block, the rectangular block for this part here. There's another rectangular block for this whole part here. And then there's this rectangular block. I mean, there's a roof on it, but it's in principle a rectangle. And then the fourth mass here is a cylinder. So if an architect goes out and designs a building, let's not talk about free-form architecture, but more the traditional architecture for the common person, you'll see a lot of buildings that are basically these masses stuck together. So one part of the solution is to have a way to procedurally describe a variety of taking masses and combining them. And then the second part is how can you add facade details, windows and doors onto these masses. And then the approach we picked was based on, based on this very successful L system work for tree modeling. And then we did probably a fair amount of modifications and changes to basically be able to model buildings with grammars. So if we look at this video, what you will see is that these four basic masses are animated in Maya, but the details get generated in a plausible, somewhat consistent way automatically. Now the animation of the building doesn't make sense as such, but almost all of these different configurations that you see animated could be used as a building in a city. So how can you use this type of work besides the straightforward probably approaches that you want to do design for games or for movies, and someone comes and says, I have nothing, I want to have a city, what can you give me in a quick amount of time? Then one of the major collaborators are archaeology. So if you look at this, then this is a virtual reconstruction of the city of Pompeii, which was unfortunate to be destroyed by a volcano. But archaeologists are interested maybe how did it look like. And so they had from excavations maybe some building footprints. And so what we did here is we took a plausible, at least that's what the archaeologists think is how it looked like, the building footprints, and we added based on the drawings that they had and different other resources they have. We tried to encode their knowledge and the variations of how this could have looked like. This doesn't mean that it's kind of unclear if the archaeologists are totally happy with the results, but this is what we think is the best guess at the end. And so you see some part is real, the basic footprints and the ideas how the building looked like, but all the details are basically generated as an estimate. So there's no way you could say, okay, this door was exactly here at, before it got destroyed, but you can say maybe this style of door was very common.
So they have maps of the streets. Are the streets laid out?
Yeah.
According to the map?
So basically we start out with GIS data and
Small thing, so in modern archaeology, they actually make a photo showing what's reconstructed versus what's real. Do you have like a photo making renderings where you show what are like the slightly different color, what are the things that are really there versus what you build the procedural scheme?
no, it was
Some
basically.
buildings are still there and some are not, and so it will be interesting to see the match between those.
Yes, I agree. But it was basically we basically didn't have the resources at that point in time to make it really archaeologically viable. It's more that we can show to them what we can do, and so now if someone has some money, they can invest it in us. But I cannot. I don't make any claims to. I don't make any claims to archaeological achievement. We also did some work in reconstructing Mayan architecture, what you see on the top, and then because when I studied urban planning, we had all these architecture classes, basically start with classical temple orders. We tried to do that. Yes.
Did you use Maya to make the Mayan architecture?
Actually, we did for the ornaments, so they should be very happy. So we basically place the windows and the doors and things like that. But this ornament that you see here, you have to create in Maya. Okay, this is maybe some work with architecture. Mainly the point, mainly to illustrate one point of the application. So if you do procedural modeling, you'll get complaints, of course, because people say, well, you create something that's not real, and we are architects, and you're insulting us. But of course, the issue is you still somehow need it. So when the architects then create some designs, they come up, of course, they're way late, they don't have any details, then they need some help that someone can make their reasonably, very early mass models look good enough so they can win multiple $1 million to actually be competitive in the visualization. So They're split. I mean, I don't want to say that that there's a huge line of architects, but a lot of architects are really interested in this. They want to push technology, but probably half of the architects will think we're crazy. I can live with that. So now we basically have this tool to write these grammars, and if you did some work with grammars or L systems, then one thing that is very obvious is these are difficult to use. You need to be good, and we saw a lot of potential there. So one of the first major obstacles was to get away from scripting, because if you do computer science, you feel that the simplest scripting should be accessible to everybody, but it turns out it's not entirely true. Even like 4-line scripts might overwhelm a large number of the population. So the challenge that we looked at in 2008 was, can we actually, with a purely visual interface, describe these architectural rules? And what you see here is a building that is still procedural, so you can take maybe the footprint and change it. You can change the building height. You maybe have some sliders. But all these architectural rules were created with a visual interface. And the second thing we looked at here is how can you basically edit. You have a procedural model, and now you want to edit something. So let's say we have the building here, and now you select this floor, which is shown in red, and then you want to change the window type manually. So you make an edit, and then the fundamental challenge in procedural modeling, it comes up in a lot of different contexts, and several other people, I guess, realize that too now, is if you then make another edit to the building, you don't want to lose the manual edit that you did before. So let's say I change the windows here, and then I change the building height. I don't want to lose the changing of windows, but of course it's, there are several design choices and trade-offs. But this is the problem that we analyzed in 2007, 2008. So this work in 2009, we tried to look at the potential to merge our work with urban simulation. So you see maybe a city like this one here, and then you want to know how is it going to grow and change over time. So maybe at one or a few time steps, it's bigger, and so on. So the work that was there before in urban simulation, very famous, is probably Urban Sim. I don't know where it started. I think it's UW, and now the guy moved to Berkeley, Paul Waddell. And what they do is they simulate urban environments on a grid base with fairly large grid cells. I think it might be 200 times 200 meters. And they only have aggregated information. So what we were interested in, can we give a plausible geometric interpretation to urban simulation? And again, this work has, I think, a lot of advantages, but still it is not finished. So this is more like a sales pitch from our side that what we think should be done in urban simulation, or what could be the next really interesting step to combine computer graphics and urban simulation. So actually for this, we basically wrote our own urban simulation system. But really the achievement from our side is we wanted to give a plausible geometric interpretation to urban simulation. So we wrote the traffic demand model and the land use model and all these things. And then hopefully if the video starts, we basically do the growth of this virtual city. What we also did is we basically took Las Vegas as a validation of our approach. And we took the maps from Las Vegas, how they were in the 60s, because it grew so rapidly. And then we grew Las Vegas for several years and kind of compared it to, see how somewhat reasonable our approach was. And I think we did okay, even though, again, this work is open for discussion. So a lot of people in urban planning, urban simulation, they are very technology averse. They don't like this type of work at all. But in several people we met, they really tried to work very hard on this. Can we give a visual interpretation how the city is going to evolve? Because in fast-growing cities that I happen to live in, like Phoenix and Atlanta, it is difficult for people just to interpret these maps that show urban sprawl, and they don't really get as much out of it as if you would basically show some visual interpretation of it. And there are urban planners, so whose goal is to basically do exactly what we did here. Just some example from a real project, bit simpler geometry, where we used similar technology. So now this is the time to honor Guaning, who is here. And I was fortunate to work with him on this project. And the project somewhat started with me knowing Eugene Zhang from OSU, and he was very interested in tensor fields, and I was very interested in urban environments. So the problem that we wanted to study is some of the relationship between fields and graphs, and I think it's a great problem that I think there are still several really important questions out there. But the overall problem is this. You have a field, how can you control the graph? So how can you go from a field, like a tensor field, to a graph? And how can you go from a graph back to a field? Now this work, we were not fully able to solve this problem. I think we did fairly well from how can we go from a field to a graph, but we were less successful in answering the question, how can you go from a graph back to a field? And why I really love this work is because somehow I love to study the urban structure of roads, but it was also giving rise to interesting challenges in tensor field design. So we came up with several novel contributions to tensor field design itself, such as some hierarchical design and several things that came from this application in street modeling. So what you see here is just some output of the street graph itself, and some 3D rendering. And then based on this work, we, as a next step, we wanted to see how can we basically look at this interplay between some pattern design and field design on a surface. So what one of my students who's graduated now looked at was, let's say I have a field on a surface. How can we use the field to basically control a pattern on the surface? And this two renderings should somewhat illustrate the problem. So let's look at the, I think it's line or Griffin model to the left. What you see here is a visualization of a curvature tensor field. It's done by placing glyphs at various spots in the surface, and based on if this glyph is cut in one or the other direction, curvatures are positive or negative, and based on the elongation of the ellipse, this shows basically how large the one or the other curvature are. And this is somewhat what we would call a local pattern. You can basically place a texture on the surface, or you can place a lot of glyphs on the surface, and people spend a lot of time studying this type of problem. So the problem that we were interested in was, can we actually create global patterns? This would be patterns that don't look the same everywhere. So even though you say, okay, we have twigs and leaves, there's some global structure how these twigs here connect. And so here what we basically did is we used some methodology from field design, and we tried to use some grammar-based modeling to basically create these patterns that are global. So unfortunately, this is when I learned that geometry is kind of hard, and this whole field design, tracing streamlines, doing all this work ends up to be kind of complicated. So I think actually for this work, students, there was like 2 years of implementation time to get that, to get that to work, with some averagely happy students. So now then, kind of try to go back, basically a similar problem to something a bit simpler, and I spent a lot of time on that last month. I really like this problem. So let's say we start with a sphere, and as part of the code that we had is we wanted to re-triangulate the sphere. We want to re-triangulate any model, and then we placed a lot of triangles. We did some greedy drawing approach, and then you end up with vertices of different valence. So what you see here is that vertices of valence 5 are shown in blue, and vertices of valence 7 are shown in orange. You could also have valence a lot higher than 7, and you could also have 4, 3. So for now, let's just look at valence 5 and 7. And then whenever we try to generate some paneling like patterns, these vertices of valence unequal 6 are extremely annoying. They always mess things up. So the problem that we wanted to work on is, can we in a triangular mesh or in a quad mesh now, can we actually control these vertices of different valence? Now this is kind of a risky topic because it's extremely simple and extremely fundamental. So it's not clear if people in the 50s didn't do that under some other name. But from the papers we studied from 2000, we actually felt that people had a misconception about how this the geometry with the valence really worked. So what we did is we spent a lot of time of coming up with editing operations that allow you to basically move vertices of a specific valence or cancel them and do things like this. Now, I don't know, what your background is, but to us this was somewhat really surprising, because everybody we talked to, they had some totally trivial answer how it would work, which was totally wrong. So, for example, I mean, maybe now you tell me that I was stupid to even think that, but you know Conley index theory or Poincaré index theory. So the trivial first thing that everybody says is, well, obviously you can cancel valence 5 and valence 7 vertex somehow. So then it's not true. that's really weird. And it's like, how is that possible? Because in field design, it's all about canceling with these indices, so it somewhat should be possible. But it doesn't work on the surface. And so we came up with a set of editing operations that we actually think is complete. This is everything you can do. We came up with some surprising facts. We had some proofs about how the whole thing worked. And so we had an editing system that basically allows us to have full control over the valence as far that is possible. I mean, there are some still annoying restrictions that just cannot be overcome. And these are inherent in the geometry, not in the topology. So even though you basically can give full control over the valence and topology in some sense, there's no guarantee that the geometry itself looks nicely. So we'll see. We submitted this work. Maybe it got killed. Maybe people are happy. So this is just the type of patterns that we're interested in and show the application of this. So if you take an architectural model like this one, and we want to have a design on it developed by our architectural collaborators, and you don't control the valence, you get lots of artifacts. So for example, what you see here is that the strips, you cannot make sure they only width 1. So what you see here is you have to place strips of width 2. That means 2 triangle strips in parallel because of the valence. You also see that if you look at the shapes that are kind of cut out between the strips, so this one here, there's one triangle, a triangle, they're all fairly arbitrary and different. Whereas if you control the valence, we pretty much get down to these hexagons and pentagons. Now, what you can also see here is, in some sense, the limitation of it, that when you just look at maybe the top here, if you control the valence, there's no guarantee that geometry itself looks nicely. So that you might have a solution that is just not ultimately what you want from the geometry side. But this was really not the problem that we wanted to study here. Again, it's more like image-based work. I mean, part of what people are interested in, they want to get reconstruction from images. So we do some remote sensing type of work. So this is a classical problem. Given an aerial image, can you go and find roads, which are linear features in it? And so you see some results here. And there we did basically classical remote sensing vision work, where we take some Bayesian statistics, and there's a local shape detection and some global analysis of a graph. Fairly classical work, but at the end, at 2007, I think we had the best solution out there for finding roads. Might be superseded by now, but we got pretty good results, which means pretty good if you go from graphics to image processing. You're always frustrated of how poorly things work. Vision, image processing, to me it's always a cursed topic. So you're used to graphics, everything works kind of well. And then if you do image processing or so, you have to lower your expectations quite a lot. And so even though the results we consider very, very good, you still see all these issues, like here there's something missing. Maybe here complete road is missing. Yes?
So this is like completely from image to the graph, or you're still doing some of the adjusting some of the number graphs?
No, this is automatic. Okay, this was also some obvious next step. If you have a procedural model, and again, because you know from computer vision that people tried for 30 years reconstructing facades. and they can't do it pretty much at all. So it's like, now it's someone else's turn to try. And I mean, still, man, this is a hard problem. And this problem is especially hard to sell to anybody because if you look at it, it sounds extremely simple. So if you say, hey, you know, I give you this image, can you just find the windows here? Then everybody who hasn't tried will tell you it's totally trivial. I can't tell you 10 algorithms, it's almost impossible to imagine how even any of them fail. But at the end of the day, things just don't work. And the problem is so difficult because just maybe look at the reflections here in this window versus this window. You say to you it automatically looks the same, but if you look at the actual pixel colors, it looks totally different. You say, well, these are obvious rectangles, but if you look at the actual gradients between the pixels, they're sometimes not even there. And you say, well, obviously this is watercolor and this is watercolor, but then you will find that the color of the frame sometimes looks more similar to the wall than the wall looks to itself. And so what we basically did here is we wanted to take some of the knowledge that we had from working with architecture and apply it to the reconstruction. And well, basically, I'm going to skip that. This is something I showed 2 years back, so we'll leave it for now. Okay, this is another really interesting problem. I like that one a lot. And I think we're one of the first to do it in computer graphics or vision. And this is in a simplified form. Let's say you have a matrix. It's regularly sampled, and you know all the entries that are shown in blue. And then you want to fill in missing values. Let's say wherever there's an X, you don't know the value. And why I wanted to do it is because I wanted to work on facade images. But I worked with a friend of mine, he liked linear algebra. So, yeah, what can you do? And you have a lot of these local algorithms. You know, you have all these PDE solvers and Markov-random fields and all that. But what we did here is it's almost more driven by methodology. It's a very modern topic in math. So we kind of tried to see how, if we start with the methodology and the application at the same time, can we kind of merge the two? So this is the basic methodology. You want to fill in the missing values such that the Frobenius norm between the complete matrix and yours is minimal. That's trivial. But then also you want to fill in such that the rank of the resulting matrix is minimal, as small as possible. And this makes sense to me because this type of rank minimization seems to be a very natural fit for an architectural model. So when you look at our best results, I mean, this is some form of advertisement because not all of them look as good. If you take the input image, which is this one, and you remove this lamppost by hand because it's kind of some structure, you remove randomly a lot of blocks so that you get an image like this. So you would then throw away this and just look at this image here, and by the low rank model as our architectural model, you're able to reconstruct something that might even be difficult to guess for a human. And so this is, we have some, well, we hope to get some NSF money for this maybe in the future. But somehow I kind of really like this. I mean, this is this idea. How you're going to solve it is you basically take the rank, and then you reformulate, and then what it leads to is that rank is non-convex, so people look at the trace norm as probably tightest convex envelope, and then do some trace norm optimization. So, so kind of our part here is we'll try to find any interesting match between an application and the methodology, and then come up with go back to the methodology, and come up with a non-trivial modification of the problem statement. So that's in some sense we try to find something where methodology as well as the application can survive. Yeah.
So is it right to think of this as like really a constraint optimization problem if you want to formulate it in that way, where you have to choose constraints and that's based on the data of your both input and output, and what you want and what you have?
Yes and no. I mean, it's kind of tricky to say. I mean, it's very. This is like a very focused. I mean, typically this is convex optimization. I mean, there are always some form of constraints, and yeah. I mean, basically, it is this type of work is convex trace norm optimization. I mean, it's. I don't know if constraint would be the distinguishing feature.
How big metrics?
Tricky. So, give me a matrix if you can compute the SVD with MATLAB, we can do it, and you're willing to wait for some time. We have the code online and some data online.
Do you have a number?
Well, whatever the SVD you can do. If you give me 20K or 20K times 20K, you're in trouble. If you give me 1K times 1K, it's probably easy. But you will see, actually, we did this work for tensors. So there, you have to go up to larger numbers than just simple images.
Do you need the whole SVD spectrum or just the smallest component?
Yeah, I mean, there's some other issues of size and then shape of the matrix and stuff like that. But I don't know if this is the critical part of it. It's I think you pretty much need to do SVD. I mean, then there's some other accelerations, but the issue is that if you do MATLAB as we did for this, the highest chance is you run out of memory. So this was our main limitation, without wanting to go to C++ and invest a lot of work. Okay, so yeah, I mean, in principle, I really love to work in procedural modeling, this type of modeling, probably especially procedural modeling. I think we came up with very efficient tools, and we learned a lot about architecture, how to encode it, but also, I mean, of course, there are limitations and challenges that I'm willing to concede. I mean, there's always somewhat this trade-off between how accurate are you, what guarantee can you give, I mean, also in image-based modeling. Different applications have different requirements, but we feel confident that at least a really large and interesting set of applications we're able to provide interesting solutions for. So now let's go to the second part, visualization and rendering. And let's start with something similar again. This is now factorization. Given the matrix A, all values known, can you come up with an outer product of two vectors that approximates the matrix the best way possible, considering Frobenius norm or 2 norm. Okay. So I posed this problem in another group to give them a chance to embarrass themselves, where it turns out no one knew the answer. This is basically a test if you have a useful linear algebra class taught. If everybody knows that, then you have a modern linear algebra class. If people don't know this instantly, then you have to look at your curriculum, I guess. So, well, but this is trivial, right? So you do SVD, and then you get rid of the singular value somehow. But okay, you can extend it, so you have a set of outer products. You still basically go at it with the SVD, but then because we had some NSF project for that, we tried to find interesting application-driven modifications to the problem so that we can get something for the application as well as for the theory. So one thing that we looked at, for example, is can you do something where we still have a sigma, like a scaling matrix, which is non-binary, but can we do factorization with binary vectors only? And so we posed this as an interesting optimization problem to look at, and at the same time our motivation came from urban rendering, where we wanted to take facade structures and basically compress them and render them from a compressed representation directly. So the idea is that if you don't look at the texture, but let's say you just have material identifier or depth, you have a lot of coherence where you have identical values. So maybe the displacement of the window, you have a larger area that's all the same. And it seems that with a binary encoding and a scaling factor, you should be able to do a lot better than just SVD, PCA type of factorization. And so this is what we did, and I think we came up with reasonable results. I mean, then there are all these system issues, how do you code the textures and all that. But at the end of the day, we were able to render something that in theory would take 100 million triangles and kind of compactly encode it. But you also see we kind of stopped the work before we go into rendering details, because you see there's aliasing and other things could be done. But we didn't go too much into that. Okay. So now then the question, and this is somewhat open, we kind of still work on that. I mean, can we find some other very interesting problem statements that we can use in an application? And so, for example, I mean, this is almost classical now. We studied that earlier, but you want to do non-negative factorization and sparse. So sparsity then usually goes into all this one norm, sparse learning type of thing. So here, then also you need to do some more. So you also want to go from matrices to tensors, because everybody is working on tensors now. You can go to an NSF panel, I'll go over the solution here. But this is just one interesting result we got in a collaboration with some biologists. Let's take a look at this fruit fly embryo image. Then what this factorization basically can do is it can find meaningful basis images that you can use. So you see these four, where you can decompose this embryo image into meaningful bases. This is not, you cannot do this with SVD or PCA. And we really wanted, and that means I really wanted to do this also for computer graphics applications, and we looked at several things. There's a fairly natural extension to volume rendering, which didn't get to implement yet, but also to some form of material editing type of work. This is ongoing work, so I'm not entirely sure what the best way to go is yet, but I'm very hopeful, and I think it's a really interesting problem.
Before you do that, have you seen Tammy Cole's work on some of the tensor factorization? She's at the San Diego National Lab, where she does these constrained nonlinear optimizations for tensor factorization to try and find missing data or multilinear structures and things like that.
Yeah, so basically, basically what how this work is structured is I work with a friend of mine who is who is mathematician by training, and so a lot of this work. Well, at least we hope it's also competitive in math, at least machine learning. But from my point of view, I also have to say that I am not able to read the papers by Terence Tao and Candace. They are entirely theoretical. Then I kind of rely on my collaborators to cover the related work part.
And have you thought about using some of this for like diffusion tensor imaging for large data sets? Because one of the problems we run into with these humongous high resolution diffusion tensor data sets is trying to find all the sum of the values and the tensors, and if you had a way to decompose and approximate those tensors.
Yeah, we did that. I mean, we looked, for example, at the paper by Schurz and Seidel at 2008. And, we came up with some ideas to improve it fairly quickly, but we didn't get around to implement it. So, I mean, we have some ideas there, but it's somewhat the issue. I feel we have more ideas than we have time to implement. So, some of the problems we almost have is that we let it rest for 2-3 years, and then someone else does it. It's a bit of a pity, but that's how it goes. So, just to show something else, we were interested in doing some mapping. Given the tremendous success of Google Maps, we wanted to basically do some research building on top of what they could do. So, in this example here, we were interested in route visualization. So, this is geared towards printout. So, you want to basically have a one-page printout that describes the whole route to you without the textual descriptions that almost always go on page 2 or 3. This was something that kind of annoyed us personally. So we wanted to basically, from a lot of our experience driving around with these multi-page printouts, we wanted to come up with something better that kind of fits on one page. And so the idea was to place detailed lenses that show the details for these points of interest, mainly turning points. And what we looked at is a lot of different design choices. Do you want to place the lenses at the border or close to the actual points of interest? How big should they be? We had different ways of doing the border layouts with breaks and non-breaks. And can we map it to an interesting enough optimization problem? So again, it's like a problem formulation for optimization. And then we also did a user study to, at least on paper, try to get feedback for a lot of our design choices we looked at. So this is something we already published, but I feel this type of work is hugely underrepresented in the Viz community. So I hope to push some more of this 2D mapping. We have some other applications in mind we try to do right now, but then probably we want to go from printouts to more handheld devices and come up with some basically new type of mapping problems. Not only route mapping, but we have a list of basically dynamic mapping tools that we think would be interesting for someone maybe going shopping or being a tourist. Some type of dynamic maps that we wanna take a look at. Okay, this work is gonna be skipped. This is some rendering and coding work we also did recently. I just want to show this one more problem. I like that a lot. Now the problem is you have remote sensing data, and then you have basically an image. Is one way to look at it. So this is an image, but instead of having a red, green, and blue value, you basically have 180 different spectral samples. And a lot of these samples are not in the visible range. So the human eye can't see the spectral response. There's really this is really not the visual type of entity. It's something that you need to visualize to show the information. So the question is, how can we come up with, you can also look at it as a tensor with 180 spectral samples. How can we take this tensor and transform it into a visible image? And here again, what we try to do is come up with an interesting formulation for an optimization problem where we say, well, we want to maybe preserve features or distances in this high-dimensional color space, and we want to keep them in the low-dimensional color space. This is one thing. Other things might be, it should be fast enough, so it kind of makes sense. And we also had this idea, if you do straightforward, right, if you know this type of work, and everybody say, well, I'll do some PCA. What happens is that PCA makes it fairly dark, right? So the idea is, even though you can kind of do something that is feature preserving, you need to still use the visible range of brightness well enough so you can actually see something. And the existing solutions are what I consider pretty bad hacks. I don't know why no one complained about it. Because what people do is they first preserve the features, and then they scale up to the visible range, basically ruining everything they did in the first step, giving you more or less random colors. So what we try to do is bring some more order to this. So what you see here is this is the correct PCA version, which would be very dark. Now you can make it bright and colorful, but then you ruin all the feature distances. And this is something we can. So this part we published. There's an extension we tried to do where we wanted to basically build a much larger system and then also incorporate additional terms in the optimization. So for example, this is the one problem. If you do this mapping, you have actually absolutely no control over the colors. So the idea is if you get this, you don't really know if this is a lake or a mountain range or a field. So the additional constraints of mapping it to more natural colors should help in this interpretation. Now, we submitted that. I think the future of this work will be to go more again into interactive tools. But unfortunately, the student left now, so I'm not sure how and if that's going to happen. But my point of view also, this is a problem that's underrepresented at Viz, but we'll see if I can effectively change that and make it more prominent. So, the rest of the work will all be skipped because of time reasons, and we go to the last slide. I have to give thanks to a lot of people. A lot of the work that I do is collaborative work. There's a huge amount of implementation. So the last paper where I did most part of the implementation was for this 2006 SIGGRAPH visibility paper. But I mainly rely on good students or postdocs to work with, such as the pleasure of working with him on one of these projects. And I have collaborators, I guess mainly in Europe, some of the US. Okay, with that I would like to close the talk and ask if there are any questions, if we have time.
So how do you add stylistic qualities in for procedural modeling so architects can express their artistic side?
Well, so at this point in time, we're more concerned about just making it more interactive for them. We are not totally at the point in time where we have robust enough tools to do more like wacky studio architecture, where architects go out and try to so one of the results I show for the valence editing is you can go a lot more crazy than that. We have some plans to try to go there, but we feel that we're somewhere held back by the large system approach to that. It's difficult to get the system robust enough and get enough tools really implemented. So we studied a lot of the architecture, also the modern freeform architecture, and we concluded that a lot of the designs are an accumulation of many different simple tools. And so then the issue is the one guy uses tapering, twist, and bend. The other one uses NURBS. The other one uses texture parameterization. One uses, and so then it ends up, we would have to implement 10 to 15 complex algorithms and the user interface for them. I mean, this is holding us back a bit. We'll see how successful we can be. Yes?
So everybody that visits Arizona State University gets a tour of the decision theater. And,
Yeah.
And so I noticed you didn't show anything on
You want me to
decision.
say on record, or you gotta be kidding?
You can hook the polygraph up.
We had some work that was shown in the decision theater, but I myself I'm not a VR type of person, and we look at it mainly as an outreach type of facility, and now they kind of go into some different directions. So we'll see how if our path will meet again in the future. Right now, probably not so much. Okay, any other?
Other questions? Let's thank Peter.
The what?
Have you published the tensor decomposition for someone? Was that in ICCD?
No, this was the 10. Well, actually, the part that I showed was the completion was at ICCD.